Okay, so get this right. We're talking particle accelerators today.
Really gets the heart pumping, doesn't it?
It's big, it's complicated, and it's all about unlocking fusion power. We're talking IFMIF-DONES.
Not the catchiest name, I'll grant you.
But hey, who are we to judge, right? What matters is this thing's designed to help us crack the code of clean energy, and get this, we're talking AI optimization here too.
Which is where it really gets interesting, even mind-blowing if you ask me.
Totally. Our source material is this dense research paper, and it lays out how AI can make this IFMIF-DONES even more powerful.
And we're not talking about some far-off future here. This is cutting-edge science happening right now.
Exactly. So by the end of this deep dive, you'll know how AI is being used to optimize these insanely complex scientific instruments.
Deep learning surrogate models, DLSMs. Cooler than they sound?
I think so. Way cooler. But before we get ahead of ourselves, let's back up a bit. IFMIF-DONES, International Fusion Materials Irradiation Facility, DEMO-oriented neutron source. Basically, it's being built to test materials for future fusion power plants. Important stuff because, well, fusion power has the potential to be a nearly limitless source of clean energy.
The holy grail, some might say.
Yeah.
But here's the catch: the materials inside these reactors. They need to withstand conditions more extreme than anything we've ever engineered before.
Yeah, we're talking temperatures hotter than the sun, not to mention the neutrons constantly bombarding everything.
It's like a tiny sun unleashing chaos on a microscopic level.
And that's where IFMIF-DONES steps in. It lets scientists recreate those extreme conditions without actually having to build a full-blown fusion reactor. Talk about efficiency.
Saves time, saves money, and probably saves a few headaches along the way.
Right, so how does it work? They smash deuterons, a type of heavy hydrogen, into a lithium target, producing a neutron spectrum similar to that of a fusion reaction.
Controlled chaos, essentially. And that control is all thanks to a series of magnets called quadrupoles.
Which are used to focus and direct the beam, ensuring those deuterons hit their target with, like, pinpoint accuracy.
You need that kind of precision when you're dealing with forces this powerful.
Absolutely. But here's the catch: fine-tuning those quadrupoles. It's like trying to solve an endlessly complex puzzle.
Not for the faint of heart, that's for sure.
Scientists rely on these complex computer simulations to find the best settings. But those simulations, traditionally done with software called OPAL, can take a really long time, like 20 seconds per simulation, which might not sound like much, but
It adds up. When you're running thousands, even tens of thousands of these simulations, you're talking days, even weeks of computation time. A real bottleneck in the research process.
And that's where the AI comes in, right? Researchers thought, hey, what if we could train AI to do these simulations way faster? And bam, deep learning to the rescue.
Like a bolt from the blue.
They trained not one, but two deep learning surrogate models, DLSMs, to act as super fast understudies for those time-consuming OPAL simulations.
And when we say super fast, we mean it. These models can predict beam characteristics up to 1,000 times faster than running those OPAL simulations.
1,000 times. That's mind-blowing. But with that kind of speed,
Yeah.
you got to wonder about accuracy, right? Can they really be that much faster and still get it right?
That's the real beauty of this research. They managed to pull it off ludicrous speed without sacrificing accuracy. We're talking error rates under 6% compared to those original OPAL simulations.
So we've got speed, we've got accuracy. But what exactly are these models predicting? I mean, we're talking about particle games here. They've got to be tracking tons of different factors, right?
You're absolutely right. It's not just about crunching numbers quickly, but what you can actually do with those numbers. And that's where our two DLSNs come in. They each have their own specialty.
Okay, so hit me with it. What makes these models tick?
Well, both of them are what we call Fourier neural operators, or FNOs for short. But each one tackles a different aspect of the particle beam. The first one, the 1D FNO, it predicts key beam characteristics along the length of the accelerator, like snapshots at various points along the beam's journey. Things like beam size at different locations, how many particles are in the beam at each point, the essentials.
So it gives us a detailed picture of the beam's behavior as it travels through the accelerator.
Yeah.
And it does it 1,000 times faster than before. I'm impressed, I gotta say. But what about the second model, the 2B one? What's its claim to fame?
Ah, the 2D model. It's like the 1D's cooler, older sibling. Imagine instead of just those snapshots along the beam's path, you could take a slice out of it at any point, like cutting through a loaf of bread, you see. See all those swirls and textures inside.
Okay, yeah, I'm getting a much clearer picture now, so it's not just a line anymore, but like a cross-section. We're talking about the shape of the beam, how those particles are actually spread out.
You got it. A 2D cross-section, and it reveals so much more about what's going on inside that beam. And you know what the best part is?
I guess it does all this 1,000 times faster, too.
Well, speed is a given at this
I know
point,
that's good.
right? But here's the real kicker. These models aren't just spitting out static images. They're what we call differentiable.
Differentiable models. Okay, you're using your science D words again. What does that even mean?
Right, sorry, jargon overload. Think of it like this. You're trying to find the highest peak in a mountain range, right? You could wander around randomly hoping to stumble on it, or you could use a map that shows you the speediest path to the top.
So the differentiable part is like having that trusty map.
Exactly. It means we can connect these models to super powerful optimization algorithms. These algorithms, they're like our mountain climbers. They'll find the best solution, that highest peak. But the model provides the terrain. It guides the algorithm towards the best solution.
I'm with you. And in this case, that peak represents the optimal settings for those quadrupoles, the ones that'll give us the best beam possible.
Couldn't have said it better myself.
So the researchers put these AI tools to the test, right? They went ahead and optimized a section of the IFMIF-DONES Accelerator, the HTS1. That was the section they focused on, if I remember correctly. Why that part specifically, though?
Well, it all comes down to manageable chunks, you see. HEBTS1, that section's got 6 quadrupoles. It's a lot of dials to turn, a lot of potential settings to explore. It's like, imagine trying to crack a safe. But this safe, it's got 6 dials, each with, say, 100 different settings.
My head hurts just thinking about it. And even with these AI models lending a hand, that's still a ton of possibilities. So how did they even begin to tackle this optimization puzzle?
Intergradient descent. It's this elegant little optimization algorithm. Remember our mountain analogy. Think of gradient descent as our trusty climber. It always takes the steepest path downhill.
So it's using the AI model to scan the terrain, constantly looking for the lowest point, which would be the perfect quadruple configuration.
Precisely. It's like having a bloodhound sniffing out the optimal solution. Efficient, relentless, and it gets the job done. And the results speak for themselves. This whole optimization process, even with all those quadrupoles and countless possible settings, took about 10 minutes.
10 minutes? You're pulling my leg. The old way took days, didn't it? This is insane. But we're not just talking about speed here, right? What did they actually accomplish with these optimized settings? Give us the juicy details.
One word, efficiency. In accelerators, you want to minimize particle loss. It's all about getting those deuterons to hit their target. And these AI-optimized configurations, they achieved a particle loss of less than 2%.
Wow, talk about squeezing every ounce of performance out of it. So they basically fine-tuned that section to within an inch of its life. But you mentioned they only worked on one section, the HEBTS1. Does that mean this whole approach, could it scale up? Could they use it to optimize the entire IFMIF-DONES accelerator?
Now you're thinking like a true innovator. And honestly, there's no reason why not. In fact, even the researchers themselves said they limited the optimization because of computational limits. Give them more power, and who knows what they could achieve.
It's like they've proven this AI approach works, and now it's just a matter of unleashing it on the whole system. The possibilities are kind of blowing my mind here, but you know me, always thinking big picture. If AI can optimize something as complex as a particle accelerator, what else could it do? What other scientific puzzles could we solve if we just pointed AI at them and said, go?
That's the million-dollar question, isn't it? This research. It's not just about particle accelerators. It's a peek into the future of scientific discovery itself. And trust me, it's looking bright.
So we've covered a lot of ground here. Particle accelerators, AI optimization, fusion power. It's a lot to wrap your head around, but I think we've barely scratched the surface of what this technology can do.
It's true. And you know what? It all comes down to training, really.
Okay, back it up a second. When we talk about AI being trained, I get that they're not, sitting in a classroom taking notes, but what's actually going on there? How do you train an AI anyway?
Think of it like this. We're basically showing the AI a massive photo album, right? Each photo is a simulation result from that traditional software, the Opalo. And each one shows how the beam changes based on how those magnetic lenses, the quadrupoles, are set up.
Okay, so it's like we're saying to the AI, look, see how these magnets affect the beam? Find the pattern, you got this.
In deep learning models, they're like that friend who's weirdly good at puzzles. They can spot these subtle connections in the data that we might miss, even with our fancy algorithms. These models, they just devour all those simulations, connecting the dots between those quadrupole settings and how the beam ends up looking.
So it's like they're learning the physics of it all, not because we programmed them with equations, but because they figured it out themselves just by looking at the data. That's wild. But okay, hold on. How do they learn, though? What's going on inside those AI brains?
All right, time to get a little technical here. These AI models are built on these things called artificial neurons. And yeah, they're inspired by the ones in our brains, but much, much simpler. Think of them like tiny little switches, all connected by wires.
Okay, I'm picturing a whole network of switches. So what are these switches actually doing? Flipping back and forth.
Each connection between those neurons has a weight, like a dial that controls how much one neuron listens to another one. During training, the model is just tweaking these weights, trying to find the right combo that lets it predict how the beam will behave based on the quadrupole setup.
It's like fine-tuning an instrument, isn't it? The AI's adjusting the strings, those weights, until it hits the perfect note. Or in this case, a perfectly optimized particle beam.
Nailed it. And just like a musician gets better with practice, the more data we feed the AI, the more simulations it sees, the better it gets at tweaking those connections, and the more accurate those predictions become.
So all those thousands of Opal simulations, they were like a crash course in accelerator physics for the AI.
Exactly. And now we've got this superpowered research assistant that can run those complex simulations in a fraction of the time it used to take.
No coffee breaks needed. But really, it makes you realize what AI could do for scientific discovery, right? Like, the
Mhm.
potential is enormous.
It really is. This is just one example, one tiny taste of what AI can do. I mean, imagine applying this to medicine, material science. We're talking about a whole new era of research, and we're just getting started.
It's pretty mind-blowing when you think about it. If AI can optimize something as complex as a particle accelerator, who knows what else it can do? This research really shows what we can accomplish when we combine human ingenuity with the power of AI. And who knows what other breakthroughs are waiting for us just around the corner. One thing's for sure, though, the future of science is looking bright, and it's exciting to be along for the ride. Thanks for joining us for this deep dive into the world of particle accelerators and AI optimization. We'll catch you next time, but until then, keep those brains buzzing.